So there are times like in our Engage from today where you have a situation like this, where Miss Chung wants to use square patches to make a baby blanket that measures 45 inches by 75 inches. She wants to use the fewest square patches possible without cutting any of them. What is the length of each side of square patch? So you're trying to build a rectangle that is 45 by 75, but you're only allowed to use squares. And so this is really a question of what is the greatest common factor. And so we have a couple different strategies that will allow us to figure this out, and some of them are more efficient than others, but our first strategy or our first method is just to list them out. And so our two numbers that we're working with are 45 and 75. And just to review, we can write these in an organized list. So we have 1 times 45. 2 is not a factor because 45 is odd, but 3 times 15 is a factor. 4, well, I know 4 times 11 is 44, and that's only 1 away, so I can't add another 4 and get to there. But I do know that 5 times 9 is another factor there. So those are all of our factors of 45. And then we'll do the same for 75. 1 times 75, no to the 2. 3, if we think of this like money in quarters, 3 times 25 equals 75. 4 doesn't work again. 5 times 15 will also get us there. So here we have all of our factor pairs for these two numbers. So with the list, what you want to do is take these and put them in order horizontally. So we have 1, 3, 5, 9, 15, and 45. Same thing for 75 rather. 1, 3, 5, 15, 25, and 75. So to find our greatest common factor, we are just going to look and see. Our common factors, we have 3, 5, 15, and 1 as well, but that's going to be obviously the smallest. So based on this list, 15 is the greatest common factor. So our greatest common factor here, that just means that on this baby blanket, if I could erase that, if we break these into squares that are 15 inches wide, we would have 3 columns because each of those 15 are there. And then we would have, let's see if these look roughly square-ish. Then these would also be 15. Did I do the right amount? Yeah, I think so. So there we go. So that would get us our square patches for our baby blanket. Now this method of listing out the factors works pretty well when the numbers are reasonable. But as the numbers increase, this becomes a really inefficient strategy with lots of opportunities to like miss a factor or have some other problems. So what we could also do is use our prime factorization and do a factor tree. And so we could call this a factor forest because we have more than one tree in here. So we'll be doing 45 and 75. So we know that 2 is, when we do our prime factorization, we want to pick our smallest factors first, and we know 2 doesn't work because it's an odd number, but 3 and then 15, so we'll circle that because we know it's prime. 15 is composite, and we're left with 3 and 5. So if we write out our prime factorization, 45 equals 3 times 3 times 5. And then we'll do the same thing with 75. 3 times 25 prime, 5 times 5, all prime. So 75 equals 3 times 5 times 5. So because we're trying to find the greatest common factor, we know that our greatest common factor is going to be the product of the common factors that we have. And so I'm going to highlight our common factors. We have 3 and 3 and 5 and 5. And so this has to be like a 1-to-1 match. We wouldn't highlight like all those 3s at once because in 45, those 2 3s are actually 3 times 3 or a 9. So you just want to kind of match them up 1-to-1. And so because our common factors that we have are 3 and 5, if we multiply them together, we get 15, which is the same greatest common factor that we had up above. So another method that we could pick is going to be, let me write down a method here. Another method is going to be a double or a triple ladder. And so, oh man, iPad on the fritz. There we go, much better. So you set this up much like you would with another ladder, but just leave some space between the two numbers, and then you get your little L. And you want to pull out any factors that you put over here on this side need to be factors of both of those composite numbers. And we know that we could do, let's say, we'll start out with 3 because we're used to prime factorizing by using our smallest factors. So you could pull out a 3, and that leaves us with a 15 and a 25. These are still composite. So if we pull out a 5, that leaves us with a 3 and a 5. So because this 3 and that 5 are prime, there's no more prime factors that we can remove from there. And so that means our answer is just going to be in these two factors that they have in common. 3 times 5 equals 15. So the only place where this diverges and is different from when we've done prime factorization ladders is that you don't have to remove only prime factors because we're just looking for what is the greatest common factor. So in class, we had an example that was, I think it was 360. What is the greatest common factor of 360 and 540? And so if we do the double ladder on this, I know that these are both multiples of 10. And so I can even pull out that factor of 10 right there because it's not going to matter in the end. I mean, if I had pulled out a times 2 and then a times 5, that would have gotten us the same thing at the end. It just would have added some extra steps in there. And plus, it's much easier to deal with a 36 and a 54 than it is to deal with the bigger numbers. So these are both even, so I am going to pull out a 2, so that leaves me with 18 and 27. And then a 3, those are both, I mean, if I really wanted to, I could have taken out a 6, but I'm going to do that actually. I'm going to rewind for a second. I know that 6 is a factor of both of these, so that leaves me with a 6 and then a 9. And 3 is a factor of both of those, so that would leave me with a 2 and a 3. So all of our common factors are right here. And so 10 times 6 times 3 is 180. So our greatest common factor is 180. Now that was when we did like the shortcuts there with some bigger factors. We could check this with like true prime factorization just to see if that makes sense or if it changes our answer at all. So if we pull out a 2, that's a 180 and a 270. Those are still even, so I'm going to take out another 2. That's a 90, and that's, let's see, 200 split in half is 100, and 70 split in half is 35. So that's 135. These are no longer even, so I can't divide by 2 anymore, but I can divide by 5. 90 divided by 5 is 100 divided by 5 is 20, and this is 2 tens less, so that's going to be 18. Nope, sorry, whoops, wrong place. 18, and then 135 divided by 5 is a 100 and a 35. 100 divided by 5 is 20. 35 divided by 5 is 7, so we're left with 27. And we can do both of those divided by 3. And so that's going to be 6. It's going to be 9. Let's do 3 again. 2 and 3. So these are all of our factors that we have in common. Let's multiply them out and see what happens. 2 times 2 times 5 times 3 times 3. 2 times 2 is 4. 4 times 5 is 20. 20 times 3 is 60. And 60 times 3 is 180. So we do end up with the same greatest common factor, but there was just a lot more steps in there. So prime factorization, you gotta pull out only prime factors, but when you're doing greatest common factor, you can just pull out whatever factors that work for both of your numbers.